Bogomolov-Tian-Todorov. Okay, thank you very much. It's a great pleasure and an honor to speak there. So I will be talking today about the deformation theory for Calabi-Yaus. Of course, for compact Keller Calabi-Yau, everybody knows everything. There is nothing to do, and this is precisely what Bogomolov and then Tian and Todorov did. So originally, I guess the idea was due to Andre Weil, who spent several years trying to fulfill a grant obligation, doing something about K3. He wanted to prove Torelli theorem about K3, and he completely failed. But in the way, he invented the name Torelli theorem, he invented the name K3, so he did a lot. And then Turina proved Torelli theorem for K3 in 60s. Unfortunately, she had an accident and died very soon, very young. And then Bogomolov completed, well, Shevarevich and Petitsky-Shapiro completed their work on K3, and Bogomolov did the same for holomorphically symplectic Keller type manifold, proving the deformation theorem. And then he had a preprint from Lefschetz, where he proved what is now known as Bogomolov-Tian-Todorov or Tian-Todorov, proving this deformation type result for Calabi-Yaus of Keller type, and then, but somehow he lost his interest to this subject, and then it was entirely differently published, proved and published by Tian and Todorov in the late 80s. This is why it is called Tian-Todorov, and what they used was, essentially they used the same argument called Tian-Todorov lemma, which holds, in fact, in open, it's a local result. It's a result about local behavior of Calabi-Yaus. So we can try to repeat it and look what happens if your manifold is not Keller and whether you can obtain a deformation theory. And this is what I'm going to do today. For Calabi-Yau, what I'm going to tell today mostly doesn't work. But you will see why. It's not complicated reason, but holomorphically symplectic is a way of, holomorphic symplectic form is a way of obtaining Calabi-Yau, which simplifies matters. So definition, if you have M-I complex manifold, and omega to form, I will use Hodge decomposition, and this means that the form is complex linear. Closed holomorphic. Well, holomorphic follows from closed, so it's a non-degenerate. Omega is called holomorphically symplective or holomorphic symplectic. Symplectic. And the whole manifold is also called holomorphically symplectic, of course. And then you can take the top power of omega, which if n is 2n is complex dimension. I mean, it's symplectic, so it has to be even. So we take its top power. It will belong to lambda 2n, 0 of n, and it is a holomorphic section, holomorphic volume form, which is non-degenerate. Then this means that Mi is Calabi-Yau. I will just define Calabi-Yau that is a manifold with trivial canonical bundle. And at some point, I will even fix the section, trivial canonical bundle. So Km. Okay, and in that situation, Bogomolov-Tian-Todorov say that the deformations are unabstracted, which means, well, for Calabi-Yau actually, so theorem, Bogomolov did it for holomorphically symplectic and Tian-Todorov for Calabi-Yau. Sorry? I is complex structure, yeah. I will use it. Thanks. So I compact Kahler, Calabi-Yau. These are two essential conditions. Reading of them, one of them is the same as reading of another, essentially. So if you don't like non-Kahler manifolds, you can just try to imagine what will happen if you try to prove Calabi-Yau for non-compact Calabi-Yau. Then deformation space. Deformation, there are several notions of deformation space, but for Calabi-Yau, they are all the same. And it's better to speak of local deformation by Kuranishi. Deformation space, so it's Kuranishi. If you want definiteness, but it's really always the same. Of I is smooth. And as always, if you speak of deformation space, there is Kadeira-Spencer map. So let's denote this by K, then you have Ti of K is mapped into H1 of Tm. This is holomorphic vector fields. This is first cohomology, and this Kadeira-Spencer map. And it is an isomorphism. In that sense, it is non-abstracted. Generally, you would, as Kadeira-Spencer and Kuranishi showed, the Kuranishi space is an embedded. It's a germ, and it is a germ which is closed complex analytic subvariety in this vector space, which is considered as a complex vector space. And the abstractions is precisely the equations which define this germ. And you can write them down explicitly. At some point, I will do it. Questions, comments? Please ask as many questions as you could possibly, because I would enjoy it very much. OK. Now, this was for Kahler. For non-Kahler, lots of examples. The best example is due to Etienne Gis, who was just looking at very simple Calabi-Yau variety, SL2C quotient by gamma, where gamma is a certain discrete co-compact subgroup. It's not hard to find many. And then he proved that this deformation space is abstracted. For this, and this sort of clearly Calabi-Yau manifold, because I mean, every Lie group has a canonical 3 form, and this is 3-dimensional, so this 3 form gives you, non-degenerate 3 form gives you a section of canonical bundle. OK, so can we do anything better? And it turns out that, so this is for Calabi-Yau, for non-holomorphically symplectic. And apparently, so far there are no examples of holomorphically symplectic manifolds simply connected, for which Tian-Todorov holds. This for very simple reason. There's just one example, well, one class of examples of holomorphically symplectic non-Kahler manifolds, which are called Bogomolov-Guan. I will define them very soon. They are compact, very explicit, holomorphically symplectic, non-Kahler. And what I am going to present is a theorem which is joined with Nick and Kurnosov that Bogomolov-Tian-Todorov holds for Bogomolov-Guan. I'm going to return to that very soon, but let me unless you have any questions, proceed to these examples of Bogomolov-Guan. Okay, so the idea is that we should start with Hilbert scheme of points. There is, the story of the whole business is the following. So Bogomolov, when he proved, there was a reason why he was disappointed in the whole direction, because he proved his result about deformation, and then he proved that they don't exist. The proof was wrong, of course, and then Baville discovered counterexamples, discovered examples of hyperkähler, and since these Baville's examples, there are no more examples of hyperkähler is the same as holomorphically symplectic, Kähler type, but since Baville, there were no examples, and what I'm going to do now is just present the examples of Baville. Okay, so what the examples have the following nature. You take symmetric power of a surface. Symmetric power of a complex surface. Complex surface is a complex manifold of dimension 2. I hope it's not surprising. We denote it by Mn with the round brackets. Of course, it is singular. But then there is a map from the Hilbert scheme to this. And by Hilbert scheme, I understand the space of ideal sheaves. I inside OM, so this ideal sheaf inside the structure sheaf, such that dimension, and here I mean just complex dimension, so its length, OM quotient by I is equal n. So the typical example is you just take n different points on your manifold, and you take the kernel, so x1 dot xn points in M, and you take the kernel, OM, goes to the direct sum of skyscraper sheaves. So the I is an example of such an ideal. Okay, and from this, it's already sort of seen that Hilbert scheme is related to the symmetric power. In fact, if you have ideal inside this Hilbert scheme, you can put this ideal to support OM quotient by I. And this support you can do with counting points, so it belongs to symmetric power of M. This is this map. Now you can easily check that this space is smooth. So Hilbert is smooth. This is because tangent space to F, to I, is x 1 from I to I, and then x0 from I to I and x2 from I to I are one-dimensional. So Riemann-Roch gives you that this is constant dimension, and it is a very well-known theorem that if you have any scheme and the tangent space is constant dimension, it is smooth. So this constant dimension, and smooth. This works only in dimension 2. In fact, if you do this Hilbert scheme formalism for dimension 3 or more, you will have lots of components. And in fact, the component which is responsible for this resolution is not the maximal dimension. But in dimension 2, everything is very nice. So you have this Hilb n of M, which I will denote by M with the brackets. This is standard notation. It goes to symmetric power, which is denoted by m with the round brackets. And this is semi-small resolution. And also, it can be obtained by a single blow-up. So in symmetric power, you have a singular subvariety, which is just a subvariety where 2 points go together, become equal, and you just blow it up, you obtain Hilbert scheme. Very simple. OK, and if M was holomorphically symplectic, then the Hilbert scheme also. This is obvious from this description, because what is holomorphic symplectic for surface? It's just trivial canonical class, so it's the same as Calabi-Yau. But what is important is that there is a multiplication from x1 times x1 to x2. x2 is one-dimensional, and this multiplication is non-degenerate. This is precisely, well, x2 is one-dimensional, of course, for when you have Calabi-Yau. Your M is Calabi-Yau, so the holomorphic simplicity of M is essential, but then you have a multiplication which is non-degenerate, skew-symmetric, and it gives you a holomorphic symplectic form. This was the result of Baville. OK, there are not very many surfaces which are holomorphically symplectic, so you can do with K3. This one example of holomorphic symplectic manifold. Another example is obtained from Tn. We are not interested in the non-simply connected guys. There is a classification reason. You can always reduce non-simply connected to simply connected. So you are really interested in simply connected. So what you do is you take Albanese map to T4. And the kernel of this Albanese map has fundamental group Z by 2 some power. And you just take universal cover. This is another example, which is called generalized Kummer. These are only examples of holomorphic symplectic which people work with. Yeah? Questions, comments? Sorry? T is a four-dimensional torus, yes. Thank you. Yeah. OK. However, it's what I told you is true. There's only 2 examples of holomorphic symplectic Kähler surfaces. There's a third example of holomorphic symplectic surface, which is no longer Kähler, which is called Kodaira-Thurston surface. Let me explain what it is. So Kodaira. Thurston is, of course, complete misnomer because, I mean, it was known since forever, but nobody cared. And Thurston was the first one who really cared about this surface. He wrote a paper in, I think, very early 80s. And of course, Kodaira classified them in early 60s. But anyway, there are too many Kodaira surfaces, so it's better to call it Kodaira-Thurston. How it is obtained? You take E elliptic curve. You take L is a line bundle, holomorphic line bundle, of course. C1 of L is non-zero. This is important. Then you take total space of L without zero section. And you take a quotient by a multiplication. X goes to lambda x. X is a vector, and lambda is a fixed number in lambda bigger than 1. So it's a complex number which is bigger than 1. So what happens? So this total space without zero is fibered over elliptic curve with the fiber C star. But after you take a quotient, C star becomes C star by lambda, this elliptic curve. So Kodaira-Thurston surface is fibered over elliptic curve with a fiber which is elliptic curve. There are 2 elliptic curves. So you take M is fibered with elliptic curve. It's called EL in this slides over E. And all fibers are the same, so it's isotrivial elliptic fibration. However, the first Chern class is non-zero. If you write the corresponding exact sequence in fundamental groups, you will see that its fundamental group is non-commutative. And in fact, B1 of M is 3. It can't be Kahler. OK. And it is holomorphically symplectic, nonetheless, because you can use a adjunction formula. The fibers of this map are elliptic curves, so they have trivial canonical bundle. The base is elliptic curve, so it has trivial canonical bundle. And this means that canonical bundle of M is a product of lift of canonical bundle from E and the relative canonical bundle from this, and this is both trivial. So this is, again, a Calabi-Yau or non-Kahler, but this is a third example of holomorphic symplectic surfaces. That's all. There are no other holomorphic symplectic surfaces except these three examples, well, up to find cover. Questions, comments? OK. So the idea, which is due to Guan and Bogomolov, well, Bogomolov probably, because Guan used an entirely different approach, that in addition to these two examples which Baville used, you can also try to do the same with Kodaira-Thurston surface. Take its Hilbert scheme and try to obtain something which is interesting and holomorphically symplectic. Of course, the Hilbert scheme will be holomorphically symplectic for the same reason, but it is not simply connected. So we arrive at a situation which is similar to taking Hilbert scheme for a torus. So now we take Hilbert scheme of Kodaira-Thurston surface. First, we can try to think about its Albanese map. Of course, it's not Kahler, so it's no good, but still makes sense. And in fact, here, the Albanese map for a Hilbert scheme of a torus is very simple to obtain. You just take every point in a Hilbert scheme gives you a point in symmetric power, and then just sum up all the points in your torus. This is the Albanese map. Here you can do the same. So if you have a point X inside Hilbert scheme of Kodaira-Thurston, here you have this map. Is it denoted some? Well, let's denote it pi. Pi, you take sum of pi of all points. So you have x gives you x1 dot xn in symmetric power, like the set. And now we take sum of pi of xi. This gives you a map to elliptic curve. So n is mapped to elliptic curve. The leaf is a divisor. The fiber is a divisor. And if you have a divisor inside holomorphic symplectic manifold, you have a canonical filiation associated with it. It's called characteristic filiation. So if X inside M, divisor in holomorphically symplectic manifold, for each X, for each point X small inside X big, you take tangent space to this divisor, and it's a orthogonal complement. And of course, this orthogonal complement is contained in tangent space because it's coisotropic. I mean, it's codimension 1. This one-dimensional. And it's not hard to see that it is actually integrable because the form is closed. Okay, so this is called characteristic affiliation. And what we do is we take this map, let's call it, does it have any name? It has a name, pi. So we take pi minus 1 of a point divisor, and take its the leaf space of the characteristic affiliation, which is dimension 1. So the leaf space of characteristic affiliation is always holomorphically symplectic. It's not a big deal. So the quotient by characteristic affiliation. Of course, it's holomorphically symplectic, but it's terribly singular, because I mean, even if your leaves of the characteristic affiliation are compact, which is what happens here, it's not hard to see that it is compact. But it's only quasi-regular. So the quotient is an orbifold. And the miracle that Guan found and Bogomolov proved is that, in fact, you can, this orbifold has a cover. I mean, in an orbifold sense, which is now no longer an orbifold, it's smooth. But it takes funny numerics. Your Chen class has to divide n. Then it works. N is this number. Okay, so definition. Bogomolov-Guan manifold is a universal cover of this leaf space, if compact, if smooth. Yeah, M is, oh, sorry, it's 2 M's now. So it should be not M here, but say Z. Yeah, because here M was Kodair-Torsen surface. And yeah, it's probably better to use S as I did on slides. But anyway. So if this is very general, you don't need any special geometric situation for that to work. But then we apply this to this particular divisor and obtain these interesting examples. This is unfortunately the only example of non-Kahler holomorphic symplectic simply connected guys. There's no other. There are lots of holomorphic symplectic manifolds which are obtained from things like nilpotent Lie groups, solvable Lie groups, and so on, but they are never simply connected. Okay. So now the result, which I'm going to try to explain, is that for Bogomolov-Guan, well, if you have a particular manifold, you can compute things about it. For Bogomolov-Guan, it's not hard because it's very simple. It's fibered and fibered and fibered with many different ways. So there are simple cohomological computations we can do. It turns out that it's enough, these cohomological computations are enough to establish Bogomolov-Tian-Todorov. There are two versions. One of them is about holomorphic symplectic deformations, another about all deformations. So they both require different assumptions. So theorem that M be compact holomorphically symplectic. Assume. So there are two conditions. That the first is that all exact holomorphic three forms vanish. And second condition is that all this H2 of OM generated by closed 0-2 forms. then deformations of holomorphic symplectic structures are non-abstracted, and they're classified by H1. Well, it's what is called Bot-Chern cohomology group. So it's by a subspace in H1 or lambda omega 1m generated by closed forms. And the second, of course, is that if this, if all cohomology classes are generated by closed forms, we're done. Then this is the same as holomorphic symplectic, and both of the statements are true for this particular example, which gives Bogomolov-Tian-Todorov. Questions, comments? Now we'll try to review how one proves just usual Bogomolov-Tian-Todorov. You will see where it diverges from the standard proof. So we didn't do much to modify the proof of Bogomolov-Tian-Todorov. There is some modification which was due to me and Kaledin like 20 years ago, but mostly it's just a standard approach, which is, I know it from Todorov, but it was popularized a lot by Kontsevich. And it's what is called, of course, physicists were mostly working with it. It's what is called the Maurer-Cartan equation. Okay, so the first observation is the following. So when we are differential geometry, you think of complex structure as of a tensor. If you are specialist in deformations, you shouldn't do that. Instead of that, you should consider complex structure as a differential operator. So your differential operator is d bar from the functions to a space which you can consider like an abstract vector bundle to B, which a posteriori is identified with lambda 0, 1 of m. But in fact, if you have this operator, you have corresponding symbol of d bar is a map from, as usual, tangent space of M to your B, to B, which is lambda 0, 1 of M. So it gives you a Hodge decomposition. This means that this operator is sufficient to give you Hodge decomposition on the manifold, and then, but it's easier to write the integrability for that operator in such a way that it becomes like part of the whole setup of differential grade algebras. So we extend this. We start with this operator, and we want it, so far the only thing we wanted it to satisfy the Leibniz rule, which is pretty much automatic if it's first order. And what we wanted to also that we write C infinity of M, d bar, B, d bar, lambda 2 of B, and so on. And to extend this, of course, you use Leibniz rule. Otherwise, it wouldn't make sense, but then it makes sense. Of course, this is the same as usual Dalbo exact sequence in 0 to n forms, in 0 star forms. Okay, and then the integrability is the same as d bar square is equal to 0. This is a version of Nuremberg. So, of course, we know from the Dalbo exact sequence that for on any complex manifold, d bar square is equal to 0. This we know, but it turns out that this is condition which is already sufficient to recover integrability. Nothing else is required. Okay. Now we should think of these guys as of, again, they're differential operators of first order. So they're the same as derivations in values in B. So the deformations, if you have d bar and d bar 1 and d bar 2, the difference between them belongs to tangent. This is derivations times B, because it's B value derivations. But since we wanted to make it different, to change the complex structure, we are not interested in the guys which preserve which has the same kernel of the simple. So we write here 1, 0. Otherwise, it will give you the same kernel of the simple. And this is called gamma. Now we can write the equation for the integrability. And this is what is called Maurer-Cartan equation. Maurer-Cartan equation. Sorry, the slides were not about this. I switched the order. I apologize about this. Yeah, but yeah, where do I have the? Okay, never mind. Probably I just lost the slide where I explained this thing. So you have Maurer-Cartan equation, d bar plus gamma or minus gamma squared is equal 0. Now you try to think about this as a superalgebra, and then the squares becomes anti-commutators, and you write it as follows: d bar of gamma is equal to yeah, it's all the way here, I suppose. Yeah, it's here. Sorry, it's different order. Minus commutator of gamma and gamma. This is the main deformation equation. It's usually called master equation. Here, this means that it is the anti-commutator of gamma and d bar. If you think of it, you'll realize that this is the same as d bar of gamma. And this is what is called Schouten bracket. Now I can go back and explain about Schouten bracket, which is something which is slightly counterintuitive, but many people know this already anyway. It's elementary. So you have vector fields, then you have commutators of vector fields. Tm times Tm, commutator goes to Tm. Let's start with holomorphic vector fields. So this is T10 of M, T10 and T10. Then you can multiply everything over T10 of M times lambda 01 of M. This is holomorphic, this is anti-holomorphic. And the important thing is that holomorphic and anti-holomorphic commute. So this would make sense to define a commutator here as well. And this is what is called Schouten bracket. Of course, now I'm slightly missing the stuff because now it will be anti-commutative, so it's really super commutator. And then you can extend it by polylinearity to the whole tangent to 0 star forms with coefficients in 1, 0 vectors. So Schouten bracket makes sense for any. In fact, it makes sense even for the polylinear vector fields, but we don't need it. So for the purpose of writing the Maurer-Cartan equation, only the usual Schouten bracket is needed, which is Schouten bracket between these two guys. But there are many nice things about Schouten bracket. In fact, what is most important that it is defined, in fact, on cohomology because it commutes with d bar. the way it is defined, it's sort of clear that it is computed with d bar, because what is written here is tensor product. It's slightly misleading, because what we do is we take holomorphic vector fields, multiply them by anti-holomorphic one forms, and then we realize that this is an algebra over holomorphic times anti-holomorphic, and holomorphic times anti-holomorphic, it's the same as real analytic, more or less. So this makes sense even if the tensor product is defined only over constants. Okay. What is important is that you can also think of Houghton bracket as a bracket of operators on the algebra lambda 0 star. So that the vector fields act by differentiations on this, and the one forms act by multiplication. But this is the same action as we were discussing when we spoke of the deformation of complex structures. So if you remember how the complex structure, how this gamma acts, it takes a derivative along the 1, 0 part, the vector field, and multiplies by a one form, 0, 1 form. So here, in this master equation, the bracket is just Houghton bracket. Okay. Now, Tian-Todorov lemma is a lemma which describes, this is a key statement, which is marvelously true for all Calabi-Yau. It doesn't need Kahler, compact, nothing. And it is a statement about expressing Houghton bracket in terms of certain differentials. So if you worked a bit with like differential algebras, graded algebras, this is what is called derived bracket. So every time you have multiplication, you have a differential on an algebra. There is this notion of derived bracket, which becomes, in that particular case, okay. So how we work with it? First, you notice that okay, T1. Tan T10 of m is the same as lambda n minus 1, 0 of m on Calabi-Yau, because we have a section theta lambda n 0 of m. This is canonical the section of canonical bundle. And using this section, we identify this and that. Okay, so this gives us a way of identifying give the following identification. Lambda PQ of M is the same as lambda P, lambda 0Q of M. This is the differential form times lambda N minus P of Tm. So, yes? It's a line bundle, so it's just nowhere 0. Otherwise, of course, it would be much more complicated question. Thanks. Anyway, so we have this identification. Now we have two different multiplications. We have multiplication on forms, and we have multiplication of these polyvector forms with coefficients polyvectors. Here it is called usual multiplication, just the Rham, and here it's called Yukawa coupling, Yukawa multiplication. But of course, you can perform it on this side. Let's denote it by this bullet. Now I will write you Tian-Todorov very explicitly. Tian-Todorov says that, so it's a statement about the Houghton bracket, gamma prime. This is a derived bracket in the following sense, that it is this usual Hodge, you have, or alpha and beta. Alpha multiplied by Yukawa with beta minus d alpha multiplied by Yukawa with beta, and minus alpha multiplied again with the cover, but d beta. And this is multiplied by some signs, which are written here, and I forgot, so I will just write plus minus. You can always recover it by using common logic, like every time you exchange something, it should be minus, times the parity. Okay, this is very important. You will see why. Because, for instance, from this result and DDC lemma, it immediately follows that the deformations are unabstracted for the usual Tian-Todorov. Bogomolov-Tian-Todorov follows immediately. So let me first remind you about DDC lemma, DD bar lemma. Okay, so if you have alpha, lambda PQ on M compact Kähler, d alpha is 0, alpha is d bar, or d bar alpha is 0, alpha is d exact, then alpha belongs to the image of d bar. This is extremely important. This is like probably the most important result from the whole Kähler geometry, at least by the number of applications. Okay, now I will compare this and that and show you why how you use that to obtain Bogomolov-Tian-Todorov. Okay, so this is something we have seen. Okay, so we are now solving the equation. The equation d bar of gamma is equal to Schouten bracket of gamma with itself. Minus, but usually people just forget about this minus. So we shall do that by taking the power series. So we write gamma as gamma 0 plus gamma 1 plus gamma 2 plus and so on. And we shall write an equation as follows. So d bar of gamma I is equal to sum. Here you have I plus j is equal op gamma r, or gamma n. I plus j is equal to n minus 1, and Schouten bracket of gamma I and gamma j. This is clearly the same equation if you write it like that. You can write it as a power series by writing here t squared, t, and then it will be just term by term version of the same equation. So instead of solving this equation, people solve that equation, which is just a sequence of equations. We're starting from gamma 0, which satisfies gamma 0 is equal, d bar of gamma 0 is equal 0, and then it will give you a cohomology class. So it belongs to H1 with coefficients in Tm. This is precisely the Kodaira-Spencer class. So when the deformation is unabstracted, now I'm slightly, I'm not proving it because it's a basis of the Kodaira-Spencer theory, but it's really important. So the cohomology class is unabstracted if and only if you can solve this sequence. That's all. Okay, so let's solve it. First, the first observation is that let's apply d bar to this guy. So d bar to the sum gamma I gamma j, I plus j is n minus 1. This is a triple commutators because you can always put d bar commutes with the Schouten bracket as we just discussed in the beginning. So you can always put d bar into this, and then this will give you like a sum of triple commutators. Gamma I, gamma j, gamma k. I'm using this curly brackets because it's really superalgebra commentators. You should really, I mean, people write, especially physicists, they really like to write square brackets. But here it becomes important because the triple commutators are always 0 of anything. This is essentially super version of Jacobi equation. So this is 0. Very good. So to solve this equation, so remember, we have just to find gamma n, which satisfies this property. But this is already closed. We need to show that it is exact. And this is precisely function of certain cohomology classes. So the triple Massey product, now we can define this cohomology class. The triple Massey product of gamma with itself is the cohomology class of this guy. So definition, triple Massey product of gamma with its gamma 0 with itself is this cohomology class of this sum gamma I gamma j I plus j is equal n minus 1 in assumption assuming that the previous Massey products are 0. So it's defined inductively. We start with the first. The first will give you d bar of gamma 1 is a square of gamma 0 with itself. We solve it. Then we do it with the third, with the second, and so on. And if we're able to solve it, we solve the deformation problem. The deformation is unabstracted. This was the usual Bogomolov-Tian-Todorov. So now how we prove it? Very simple. So far, I think this is true for general, but we want to prove something. And for that, we need Bogomolov-Tian-Todorov lemma and the d bar lemma. Let me explain how. OK, so we're solving this equation again. We can start, since now we live in Keller, Calabi-Yau, we can start with gamma 0. We start with cohomology class, so it's lambda, it's in H1 with coefficients in Tm, which is the same as H1 coefficients in omega n minus 1m. And this is H1 1n minus 1. And we take harmonic representative. Then d bar of gamma 0 is equal to d of gamma 0 is equal to 0. OK. Now what we do is we solve this equation step by step. And at each point, OK, so gamma 0 commutator with gamma 0 by Tian-Todorov is equal to d of gamma 0 multiplied, UCAL multiplied by gamma 0. So it's already d exact. It has 0 cohomology class, and it is closed. You can use d bar lemma and obtain that it belongs to the image d bar. And then you choose your gamma 1 such that it is d exact using this. And then you repeat. At each point, you solve this equation using additional constraint that your gamma n is d exact. By using at each point, what you have is that it is d closed and d exact and d bar closed. So you can apply DDC lemma, and you obtain that this sum is in the image of d bar. This means that you can choose your gamma n, which is not only which is in the image of d. And then you can repeat it, and at each point you obtain a closed your cohomology class is exact because of DDC lemma. So this is how you do, you prove how you solve this Maurer-Cartan equation. You really use, at each point you use the, yeah. So what I didn't write, it's in the slides. You can write explicitly this by writing, okay, we already assumed that at each point this gamma I are D exact. So we write it, then these two terms are 0, and this becomes D of sum gamma I, you can multiply it by gamma J. So this term is already D exact and D bar closed. Using D bar lemma, you can solve it. Okay, so this is in a Kahler setting. I don't have much time, so I will be very short and try to explain how you do that with non-Kahler. So the point is that now it's even simpler because you have this identification between Tm and omega n minus 1, but now it's actually omega 1. It's holomorphically symplectic. Tangent is cotangent. So there is a version of Tian-Todorov lemma which is even simpler than this because it doesn't need Yukawa coupling. And it, instead of Yukawa, it has this So you have holomorphic symplectic form. You can form Lefschetz triple with this holomorphic symplectic form. And with this Lefschetz triple, you can write like L omega, H omega, and lambda omega. And you can write delta, which is commutator of D and lambda omega. So instead of having Yukawa and D here, you write the same, but with the usual product and delta. Okay. And then now, of course, we're in slight trouble because the closedness, so the closedness here is already non-trivial, that we can represent it by harmonic form, which is declosed. There's nothing, no reason at all that will happen for non-Kahler manifold. But instead, we notice that for holomorphic symplectic deformations, instead of usual forms with coefficients in vector fields with coefficients in forms, we have Hamiltonian vector fields with coefficients in forms. Hamiltonian vector fields are much better. And then this Hamiltonianity becomes closedness of the form representing this class. So this is another ingredient which helps to establish this. This is Maurer-Cartan for Hamiltonian vector fields. You rewrite it very simple, but it becomes now very much more explicit. Okay, and in the end, what we obtain is this explicit proof. So you just we use Bogomolov-Tian-Todorov as previously, and we start with the form which is now we have Hamiltonian vectors field here, so it's already declosed by construction, and then we solve this equation using the now it's an equation about it's an equation about 2 forms and 3 forms. And the assumption which I gave in the beginning is an assumption about 2 forms and 3 forms. This is precisely the assumption you need to do this successive DD bar lemma for this very small cohomology. This is the advantage of using holomorphically symplectic over Calabi-Yau, because for Calabi-Yau we would have middle cohomology, and here you have first, second, and third cohomology, which are much more accessible. Okay, that's all there is a proof, but I don't think we have time to discuss it, so thank you very much.